Ladies and gentlemen, we would like to welcome you to the webinar today about chromatography column packing for manufacturing, benefits for dynamic axial compression. My name is Herbert Enger. I'm the product manager of the process hardware at Bio-Rad Laboratories, and we're very pleased to have you here on board today. We will have one of our experts here giving the presentation. It's Kim Brizak. She is the manager of our applications laboratory, and over the past years she was working in biopharmaceutical field and a lot on downstream processing, held various positions, and gained a lot of experience in column packing with different types of columns, with different media types, no matter if it's compressible or incompressible media, if it's open columns or closed columns in a contained system. And we believe that she will just give you a lot of information, a lot of hints, and a lot of recommendations that make your daily life easier when you work on your columns and when you work in your facility. At the end of the presentation, we are going to have a question and answer time. And we would like to encourage you to ask your questions submitted by typing the questions in the box on the lower right corner of your screen. We will ask Kim then to respond on these, and I think for now it's time to give it to you, Kim, and hand it over here.
Hey, thanks a lot, Herbert. Looks like we have a good set of people that are attending today, so welcome, thank you. And let's get started. So basically, scaling up and scaling down are two things that are very important in process chromatography. And so scaling up is actually very well defined. There's a lot of full-time positions at companies for this responsibility for process transfer. And a lot of conferences actually include full sessions on this topic. So for the most part, the chemistry stays the same, so the resins and the buffers are going to stay the same, but the type of equipment is what changes. Once the manufacturing scale is licensed, the small scale needs to mirror the production parameters. This is used for discrepancy investigations and validation, life cycle validation, viral clearance validation, all of these things that are done for process chromatography. So any changes that are made at manufacturing scale need to be appropriately scaled down for troubleshooting and continuous improvement. But a lot of times the procedural differences are overlooked. This is because we know that the chemistry stays the same, and so we don't necessarily look at the procedural changes that need to be made between laboratory scale and process scale. But if we look at the differences, so this is scaling up from laboratory scale to pilot scale. We see at a laboratory scale is generally in the diameters of about 0.5 centimeters to 5 centimeters. This is always an open column system, meaning that you have to take the top off, top flow adapter off, pour the resin in. You usually do flow packing and then just manual compression. When you get to pilot scale, this is up to about 20, maybe a little bigger centimeter diameter, depending on the size of your process and how many kilograms you're processing at a time. But the procedure is essentially the same. You have to take the top off and pour the slurry in and either do flow packing with manual compression. So on the left we have the same thing. You have a little bit bigger pilot scale. It's still an open column system. But then when you get to manufacturing scale, you can get up to 2 meters in diameter. And at this scale, you're going to typically see pack-in-place technology, which means that the top piston is not removed. This is for a number of reasons. It can be very heavy. Oftentimes you need a hoist for that, and a lot of companies don't have hoists in their manufacturing area. Also, a lot of times people want closed systems, so you don't want to be taking the top off in a processing area. The second issue with process scale is that reproducibility is really critical. It's less critical at pilot scale and laboratory scale because you're only doing a few runs. So the bed may not need to be stable for that period. But processing scale, you're looking at doing anywhere from 10 to 100, sometimes 200 runs on a single pack of a resin. So reproducibility is very critical at this point. So what does it mean to have a well-packed bed? Well, as we know, the media that's used for process chromatography is not monodisperse. So there's always a range of particle sizes. We have heavier particles and lighter particles. So if these are allowed to settle, the heavier particles will fall to the bottom. And you can see this is a slightly darker shade here on the bottom, and the lighter particles on top. The flow direction for most process columns is going to be in the axial direction. Axial means it's up and down rather than in the radial direction from side to side or from the center to wall. So if we're doing upflow at any point, or some of these particles can shift and you can have movement within the bed if it's not well packed. So what does it mean to have a well-packed bed? Well, the goal is to consolidate all of the media so that it's homogeneously distributed between the top and bottom and from center to wall. So why do you need a well-packed bed? Well, as we said before, reproducibility is important for process consistency. You don't want lot-to-lot variations, and you don't want packing-to-packing variations. And you want that bed to be stable over a long series of cycles. You also don't want further compression during operation. So during the buffer cycling, or the cycle that you use the column for, you can have swelling and shrinking of the beads. If you have high salt buffers, or if you have ethanol, this can cause changes to different types of media. Also, the higher viscosity buffers, like the sanitization, the high 1 molar sodium hydroxide, can cause further compression. And so when you have the further compression, the bed then relaxes, and it can cause some variations in the packing density, or the homogeneity of the packing. The irregularities in packing can also cause uneven flow, and any changes in flow can lead to increased back pressure, which is can be a problem, especially at process scale when we're typically working at fairly low pressures. And it can also lead to changes in retention time of an elution peak, and also the sharpness of the peak. So all of these issues can lead to changes in product yield and product quality. And we know that consistency is by far the most important thing in manufacturing. So why is column packing for manufacturing considered so difficult? Well, I think by virtue of how many people we had sign up for this webinar today, it's something that's not very well known. It's not done very often. Usually it's only a few times a year, hopefully. You're not having to pack a column before every lot. There's usually very little experimentation because you're in a GMP processing area, so your quality groups and your regulatory groups aren't going to let you just have free rein for experimentation. Also, media is pretty expensive, so you can't just be doing packing studies on media and then throwing it away. You want to be able to use it. So because of these reasons, column packing for process chromatography is often considered an art. And in almost every article that you read on column packing for manufacturing, you're going to see this phrase, is it's often considered an art rather than a science. So there's usually only a few people in the company, if at all, that really have an understanding of column packing. And if you have any constraints at all, if you have a different type of column, or maybe the ceiling height in your processing area is a little lower than what you would like, the equipment footprint, how big your pump is, the range of flow rate, all of these things that you may not have what the vendor considers ideal for packing. So you may have to make some modifications. Finally, there's a lot of new types of media that are out on the market now, and the base bead really can make a difference as far as how to pack. So there's no universal procedure for packing chromatography media in general. Finally, tight deadlines always require getting it right the first time. So this is often overlooked when you're getting ready for your processing. You've got everything in place. You've got your buffer validation done. You've got your your elution profiles that you need to look at, and you save the column packing until the last minute, and it needs to get done right the first time. You don't have time for repacking. So how do you get a well-packed column? Well, there are a lot of equations and theories and publications that discuss the science of packing, like I said. A lot of these are academic in nature to understand the physics of column packing. In fact, a lot of these articles that you can find are actually in regard to HPLC columns, where it's very critical to have a well-distributed bed, but it's also not necessarily helpful when you're talking about packing a column in a manufacturing area. But there's a few concepts that I do want to go over so that we're all sort of on the same page. A little bit of this might be old news to you, but some people may be seeing this for the first time, so I want to make sure that we're all on the same page. We want to talk a little bit about pressure flow, what critical velocity is, what is wall support and what does that mean, and then headspace and compression factor. So here's a graph on critical velocity, pressure flow. So what we see is for this particular resin, we see a fairly linear relationship between pressure on the left, this is in bar, and linear flow rate in centimeters per hour. And up to about 250 centimeters per hour, we have a linear relationship. That is, for every increase in flow rate, we see a increase in pressure. Once we get past about 250 centimeters per hour on this particular resin, we see that the pressure actually increases nonlinear, and we get an increase in pressure without even increasing the flow rate. The point at which this curve shifts is called the critical velocity. Now, this is typically done by your manufacturer. You don't want to be doing this in your processing area to find out what the critical velocity is in your column on your equipment, and the reason for that is for a lot of media, the high back pressure can cause irreversible damage. So this is typically done by a media vendor in order to know what the critical velocity is. This is a study that was done a number of years ago, a little over 12 years ago, over 10 years ago. It's often, you hear a lot about it, it's referred to a lot by Stickle and Fotopoulos. And what they showed was that as you increase the diameter of the column, you decrease the wall support. So that means in a small column, laboratory column, there's more surface of the media that is in contact with the wall. Now the wall provides support, and so actually you have better pressure flow attributes at smaller scale than you do at larger scale. So in this example, what you see is all the way to the right, the blue curve is in a 20 centimeter diameter column, and you can get out to about 170 centimeters an hour for this particular resin before you reach the critical velocity. But in a larger column, a 2 meter column, that's the red line all the way to the left, you can only get to about 130 centimeters an hour before you reach the critical velocity. This is with the same resin, same bed height, same buffer. The only difference is this diameter of the column, and this is very well known, and it's been shown several times since then. You can imagine even at laboratory scale, even smaller, all the way, the curves move further to the right. So what you see when you're developing a process is not necessarily what you're going to see when you get into manufacturing. So how do I pack this resin in this column? You've got, you're scaling up, you've got a piece of equipment, and you've got some resin. Well, you typically take whatever instructions you get from the manufacturer of the column. Usually the media vendor will have some advice for you as far as how to pack that media in a production scale column. And sometimes you've got a little bit of in-house experience, somebody that's packed a lot of columns at the manufacturing scale. And you mix those all together. And what you cross your fingers, and then you hope that you get a procedure that works right the first time. Well, that doesn't often happen. It takes a lot more preparation than that. So historically, what people have done and what companies have done is they've used flow consolidation. So you hear this a lot, and in my research for this presentation, I found a lot of different advice, a lot of different types of advice. So some companies say go for shoot up to 3 times the maximum processing flow rate. So let's say your load is being done at 200 centimeters an hour. Well, now you've got to pack your column at 600 centimeters an hour. Some of them say 85% critical velocity, or anywhere from 65 to 90% of the critical velocity. Well, you don't know what the critical velocity is in your manufacturing column unless you actually do the pressure flow curve. And like we said, sometimes that can damage the media. So it's not recommended to really do that in your column. There's also recommendations to use a pressure set point to compress the bed. So you often see, make sure that you use 4 bar while you're compressing the bed. Finally, you also see packing and buffers which can cause maximum shrinkage. So for a lot of media, ion exchange media, typically 2 molar salt is a buffer that will make the beads shrink the most. This is so that you're packing it as tightly as possible. And when it goes into a different buffer, like an equilibration buffer, and it swells, then it's not going to produce any headspace. Well, a lot of these packing recommendations are actually developed at laboratory scale and then transferred with minimal procedural changes because there's very little understanding of what the dynamics are at process scale. So in flow packing, which is probably the most commonly used, especially for pilot scale, we're just going to go through this very quickly. I'm sure many of you have already performed this type of packing, but you take the top of the top flow adapter off, and you just pour the slurry into an open column. And then once it starts to settle a little bit by gravity, you put the top adapter back on, and then you consolidate by flow. So you have a process pump. It's usually a type of skid, or sometimes you can use just a separate pump, and you apply downward flow in order to consolidate the chromatography bed. Finally, you move the piston down. It's usually done manually with a hand crank, and it often requires several cycles. So sometimes you have to apply flow and then lower the piston, apply a little bit of flow, lower the piston, and it needs to be done in several cycles. It's rarely done in one step. So what are the advantages to flow packing? Well, it's very similar to lab scale, and most pilot scale is performed this way. In general, you have a more homogeneous bed than if you just let the particles gravity settle, and you can control the bed compression. So there's some good advantages. There's also a lot of disadvantages. So for instance, as we discussed earlier, it's very difficult to remove the top piston when you get to the larger scales. Like I said, you may need a hoist, or you may need several strong people to lift that top, and then strong people to put it back on. Also, you have the gravity settling that happens in the meantime, which can cause some heterogeneity in the bed. As we said, if you're using a 2 to 3 times the maximum processing flow rate, up to, let's say, 600-700 centimeters per hour on your column, most skids that are made for a certain processing range aren't going to be able to go that fast. So you may need a larger pump than what your processing pump is. The other issue is that when you get to these higher flow rates, you can get much higher back pressure. So the example that I showed earlier where the critical velocity was reached at 250 centimeters an hour, for some resins, the critical velocity isn't reached until well over 1,000 centimeters per hour. So I don't know very many companies that have pumps that can operate at that speed. It's pretty rare. Next issue is that some of the flow adapters for these types of columns are optimized to have evenly distributed flow when it's close to the bed. So it needs to be close to a bed in order to have nice uniform flow. If it's not close to the bed, usually you'll have more flow coming from the center where the central distributor is. As we said, it often requires multiple steps of lowering the adapter, flowing, lowering the adapter. This allows for that relaxation that we were talking about earlier, which can be non-uniform and can cause voids and variations in the bed. Finally, when you're packing the small particles, you may have a denser bed at the bottom than at the top. And this can also happen due to the extra gravity settling time while you're replacing the top piston. So the next type of packing that was introduced at process scale when columns started to get bigger and bigger is stall packing. And this is probably well known to a lot of the people that are attending. And it essentially involves having a fixed height adapter. So you start with the piston on top of or in place at its bed height. So if you want to pack to a 20 centimeter bed, for instance, you would set the adapter to 20 centimeters. you have a slurry tank, and it's attached to a diaphragm pump and a pressure gauge. And there's generally two different ways to introduce slurry into the column. You can go through the bottom or through the top. In this example, I have the slurry tank and the diaphragm pump attached to the bottom. And there's a central nozzle that comes up out of the bottom of the column or out of the top. And then the slurry is pumped through the diaphragm pump, while the resin is trapped by the frit, and the fluid or the flow comes out the top. It's often done from bottom to top in order to be able to remove any air that may be entrapped under the frit. So this is usually the most common type. And then when the pressure gauge overpressures, you know that you have a packed bed. This is the general type of stall packing. There are some variations, but this is just the general method. So there are some advantages to stall packing. As we said, it's generally a fixed bed height, so the column tube height is limited. That means that you don't really need a very tall ceiling in your processing area. It's only one packing step, so you don't have the multiple flow, lower the adapter, flow, lower the adapter, etc. It's only one packing step, and that can be automated. The packing pressure, so the pressure at which you set the pressure gauge to overpressure, can be varied depending on what the media characteristics are. So if you have a pressure that, a media that needs to be tightly packed, you can go to a higher packing pressure than one that doesn't need to be, it has a lower compression factor, I'm sorry. It's a really fast process. If you've ever done this, it's generally like 5 minutes or less because it uses a very high velocity. Some of the more recently designed columns within the last 5 to 10 years have the capability for hydraulic movement of the piston following the pack for additional axial compression, but this is generally kind of clunky. It's not very precise, and it's not very smooth for the most part. But you can do additional compression. So what are some of the disadvantages? Well, it doesn't scale very easily. Actually, since you have that central nozzle delivering media to the sides of the column, a lot of times there's very big differences seen between, for instance, a 45 centimeter column and a 60 centimeter column, which is not a very big difference in scale, but can really change your packing procedure. The diaphragm pumps can also cause some damage to the media, not necessarily one time through the diaphragm pumps, but a lot of these procedures for these types of columns call for recycling the slurry through the column, or I'm sorry, through the diaphragm pump in order to prime the lines. And for some media, this can be damaging and can cause fines. For stall packing, you also need to use a pretty thinner slurry, usually less than 30% for this type. And so that means you need a larger slurry tank and more buffer, which generally just means more money and more footprint in your processing area. You also need a media overage, so you can't deliver the exact amount. Most procedures call for 5 to 10% media overage, and the media can cost a lot more than the column itself. So this can be a problem for companies that are trying to economize. The unpacking procedure also takes a lot of buffer. It can take up to 10 column volumes of buffer, and as we said with the slurry, this means it's just a bigger slurry tank and more buffer, which can be very costly. If you're trying to recycle the slurry into the column to do the unpacking, then you can also damage the media at that point. So unpacking is not the easiest thing to do in this type of column. One of the most important things is that the slurry is going through a central nozzle, and so it's delivering from the center out to the sides, the walls, and this can lead to variations in the radial density, which is from center to wall. These are far more detrimental than any variations in the axial density of the beads, and so if you can imagine, if you have a void somewhere in that area or a denser region, that those can all cause shoulders or double peaks, things like that. Finally, the bed compression can be really variable, and I'm going to explain why that is. If we look at the next slide, this shows us the difference between consolidating a bed with constant flow versus constant pressure. So On the left-hand side, if we have the same flow, we see that the pressure is changing the whole time until it evens out. So the pressure starts off very low as the bed is consolidating at the bottom. The bed is just starting to build, and as the bed grows from 1 centimeter, 10 centimeters, the higher the bed height, the higher the pressure. So even though the flow is the same, the pressure is increasing the entire time. On the right-hand side, what we see is that as you increase the pressure, as you maintain the pressure, the flow is going to decrease. So it's the same principle, it's just that you, as the bed is consolidating or as the bed is compressing, you'll see a decrease in flow. So what have we found? The packing by pressure is actually not very reproducible. First of all, it doesn't transfer well from lab to process scale. As we see with wall support changes, the back pressure is going to change pretty significantly in some cases. So you can't transfer a process of packing by pressure from laboratory scale or even pilot scale to process scale. This is going to give you some differences in compression and differences in back pressure. There's a lot of other factors that can influence back pressure. The particle size distribution is actually really important, and what we see on the right is the effect of particle size. Now, as I said, most process chromatography media has a particle size range for the distribution. And so even though the mean particle size might be 50 micron, that mean might be 47 or 52 or anywhere in that range. And the actual range of the particle size can be huge. It could be like, let's say, 30 to 70, for instance, or even bigger. So a very small change in the mean particle size, on the right we see 50 micron, and on the left in the pink we see 45 micron, actually has quite a big impact on the back pressure at the same flow. We see at 300 centimeters an hour, it's almost twice as great for this particular resin. Other issues or other factors that influence the back pressure are the bed height. The taller the bed, the higher the back pressure. The viscosity of the packing buffer, so if you're using a high viscosity buffer or a low viscosity buffer, that will change your back pressure. What type of frit you're using. So at laboratory scale, you're often using mesh frits that are made out of polyethylene or polypropylene. And at manufacturing scale, you might be using stainless steel. The porosity is also going to make a difference. The skid piping diameter, so the skid that you're attached to that's doing the flow or the pressure packing can change from small scale to large scale. And also the distribution type, so the column flow. There's different types for different types of manufacturing columns, and that can really make a difference on your back pressure. So with inadequate packing, we'll see further compression at higher flow rates. So we see here, starting at a little over 100 centimeters an hour, there's a little bit of headspace that starts to form. So if we, this blue line is basically the bed height of the column, which if we pack the bed to 20 centimeters and we increase the flow, we see that the bed height will decrease, so down as much as 18.5 centimeters. So a loss of 1.5 centimeters, which is pretty significant. And as we said, this allows for non-uniform relaxation and can cause variations in the bed. The headspace, as we talked about, can also be caused by shrinkage due to buffer changes. So this is an interesting question, and I'm sure a lot of you have dealt with this before, but we all know how to calculate a column volume. It's just the volume of the cylinder, pi r squared times the height. So here's an example. We have a column that's 45 centimeters in diameter, and we pack it to 21 centimeters. So just by basic geometry, the column volume is calculated to be 33.4 liters. Well, let's say you have some high flow, you have a little headspace, or maybe your asymmetry is tailing, and so you decide that you need to compress the bed a little bit more. So you just lower the piston a little bit. Now it's 20 centimeters instead of 21. You haven't taken any resin out. You haven't changed anything inside the bed other than the compression. But now your column volume is calculated to be 31.8. So what's accurate here? What's the most accurate thing that we can describe when we're writing in our SOPs and submitting documents to our regulatory agencies. How do we define this? It's a pretty commonly asked question. So, is there a better way to pack the column? Well, what we've shown is that packing by pressure or flow can lead to variance in bed compression and therefore variance in the column volume. This will definitely affect your packing reproducibility and your bed stability. Correct compression is critical. As we've shown, that incorrect compression can lead to poor column efficiency, can lead to changes in your elution peak retention time, also the shape of the elution peak. It can lead to changes in relaxation of the bed, uneven flow. If you're over-compressed, that can also lead to problems because that will affect your back pressure. It might also affect your bonding dynamics during processing if there's any change to the pore size on the beads. So what is compression factor? Well, it's pretty simple. It's settled bed height divided by packed bed height. I usually like to remember this as SOP, or settled over packed. It's the easiest way for me to remember it, and I hope it gives you an easy way to remember it too. So, for instance, a non-compressible media will have a compression factor of 1.0. So, settled bed, 20 centimeters. Packed bed, 20 centimeters. Anything that's compressible will have a compression factor greater than 1.0. So a lot of media is going to be in the 1.1, 1.2 range. I've seen as high as 1.6 to 1.7 compression factor, which is highly compressible media. You get this number from your media vendor, and it's usually going to give you the best performance and the best stability for a packed bed. I want to caution you, though, not to use percent compression. This was commonly used a few years ago, and it was very well used all the time. And you would hear, use a 20% compression for the bed. But that can be a little bit confusing because it can be interpreted a couple of different ways. I mean, we can interpret it as going from an original height of 120 down to 100, or you can interpret it as going from 100 to 80%. So in the first case, 120 divided by 100 is 1.2, but in the second case, 100 divided by 80 is actually 1.25. And the difference between 1.2 and 1.25 is about 20%. Now this may or may not be significant for some resins. Some resins have a nice range. They might be, 1.1 to 1.2 is a good range for the compression factor, but some it should be very specific. As we also discussed, resin can shrink or swell in different buffers, so you need to be aware of what the compression factor is in your specific packing solution. If you're packing in a basic solution, that may give you a very different compression factor than if you're packing in an acidic solution or a high salt solution, for instance. So you need to be really aware of when somebody gives you a compression factor, what buffer is that compression factor for. So here we see the pressure flow curve as well as a Headspace measurement for different compressions. And the blue is a low compression. It's about 1.13 for this particular resin. And what we see is that starting at around 200 centimeters an hour, we see a decrease in Headspace, and it can get quite significant as you go further out. But at the higher compressions, in the pink and the green lines, 1.2 and 1.26 respectively, you see that there's a pretty stable bed height, that there's not much change in the bed height at the higher flows. Another thing to notice here is that the green curve, 1.26, gives a little bit higher pressure than the pink curve at 1.20 compression. Now either one of these, there's not a significant difference in the pressure flow curve. So either one of these would be acceptable for a packing process. So in this case, you would have a range of what an acceptable compression factor is. But you definitely want to be over 1.13. So how do we calculate how much resin we have? I mean, packed bed height is easy. As we said, that's just going to be wherever your piston is, that's going to define your packed bed height, right? But what about settled bed height? So how do I figure out how much resin I need to put into the column? Well, using measurements from your packaging is not always accurate. First of all, most media vendors are going to put in just a little bit extra into each container to make sure that they're not shorting their customers. In this case, that can result in slight overages. Another thing is that you often have to remove whatever the shipping buffer is. So if it's shipped in 20% ethanol, that's usually not going to be your packing buffer, so you need to decant and replace with packing buffer. This might result in some loss of the slurry before you get to the packing stage. In some cases, you may need to define the media, which means you need to take off the fines before you put it into the column. This can also cause differences in what your measured slurry volume is. So what would be ideal is if you could just transfer everything you want to pack into the column, and then you just let it settle overnight in the column. That would be ideal. Then you'd know what your settled bed height is. But it's not very practical. There's a couple of reasons. Obviously, you'd have to repack the column. Also, you'd have to transfer in, you wouldn't know beforehand how much you needed to put in the column. You would just transfer what you thought you needed to put into the column. So there's a couple of different methods that are used for measuring slurry density. One of the most common is using a graduated cylinder. So you'll take a large graduated cylinder, maybe a liter or a 2-liter graduated cylinder, and just transfer a section of the media or the slurry into the graduated cylinder, and then you let it settle. Well, for some media, this might take overnight, especially like high-performance media, HP media. It can take a really long time to settle. Also, the wall support, because the graduated cylinder is much smaller, may introduce variance. Not much, but a little bit. So this isn't very accurate because you don't want to, or I'm sorry, it's not very helpful because you don't really want to take a long time to let your resin settle. There's also a method called the rebound method, and in this case what you do is you would transfer the media into the column and apply flow or axial compression. Then you'd stop the flow, allow the bed to relax, and record the rebound height. This is helpful for some media, definitely. It's clearly not possible in a stainless steel column because you can't see what the height of the bed is. It's also not predictive, as I was saying in the case of the first method. It's not predictive. You have to transfer everything first. So if you transfer everything and you have 10 liters more than you wanted to have in there, then you've got to start over again. It's also not very practical for highly compressive media. The media that I was talking about earlier that has a very high compression factor, once you start applying compression, you cannot stop applying compression. It really leads to big voids in the bed, and it's a lot of variations in flow. So it's not always accurate for some types of media. Useful for some types, but not all. There's also the centrifuge method. So what you do is you take a small portion of the slurry and put it into some spin concentrators, and then you centrifuge the liquid out. You weigh the liquid and the slurry separately on a small balance. And in this case, what you would do is convert the gram per gram percentage to volume per volume percentage. This can actually be quite accurate, but you have to do the conversion factor beforehand in a laboratory in order to correlate what the gram per gram percentage to volume per volume percentage is. Finally, this also requires additional equipment in the processing area. A centrifuge is not something that's very common in a purification area, so it's a little difficult to use that across the board. One thing that we use quite frequently here at Bio-Rad is a drip column. So basically, you would take a small drip column, put your slurry in there, mark the total slurry height, and let it drain. So I'm going to show a picture of that in the next slide, but it's very quick, 10 to 15 minutes usually. It doesn't require any expensive equipment, so that's nice. You may get some variance due to wall support, but it's usually not significant. So here's a picture of what I'm talking about. These are drip columns, so they come empty, and they come with a little snap plastic piece that snaps off the bottom here. So what you would do is dose your slurry into the disposable column, and then you mark the total height of the slurry. I don't know if you can see these little lines here where I'm marking the top of the slurry. Then you snap off this bottom piece and just let the liquid drip out. It usually takes about 10 to 15 minutes. And when you're finished, you just measure the total height of the slurry, and the total height of the resin that's left in the drip column, and divide that by the total slurry that you put in there. In this case, we did it in triplicate, so you see there's slightly different values here. This one on the left is a little bit higher, and that has to do with the sampling procedure and so forth and so on, but you want to do it at least in triplicate. And it typically gives us within plus or minus 1% of what we measure in the column when we actually let the resin settle overnight. So this is a nice, effective way to do it. It doesn't require expensive equipment, and it's pretty quick. So once I know my slurry density, how do I develop a packing method? Well, first you calculate your target column volume, and we always recommend to use a range. 20 plus or minus 2 is a pretty common range. So then you have to know what the compression factor is for your media. For this example, it's 1.20, and so you calculate the amount of resin that's required. You multiply the target column volume by the compression factor. And we're not going to do column volumes here. I can just do height. So if your packed bed height is 20, then your settled bed height should be 24. It's just 20 times 1.2. And then you determine your slurry percentage. So let's say it's 50%. We'll make it very easy. And then you calculate the amount of slurry to transfer into the column. So in this case, the slurry height, the amount to transfer into the column, is 48 centimeters. It's the amount of resin required divided by the slurry percentage. For dynamic axial compression columns, what you do is transfer that amount of slurry into the column. And you can transfer this slurry, you can do it either via suction, so where you start with the top piston all the way down at the bottom and move it up, move the piston up slowly. In this case, in the Bio-Rad case, the slurry valves are on the side of the column. And so the slurry enters through this valve on the side while the piston is being moved up. Once the slurry has been completely introduced into the column, you close the slurry valve and you start moving the piston down. The piston is controlled by this motor on the top here. It's controlled, both the height and the speed of the piston are controlled by this motor. And it's really, the only critical speed that you need is that it needs to be faster than the gravity settling rate of the media. So in most cases, this is going to be less than 300 centimeters an hour. And you can do this with the top closed and the bottom open so that the flow comes out the bottom. The liquid packing buffer comes out the bottom. And then you go to your precise compressed bed height using the piston. So a couple of points about this. It's really ideal for compressible resins. It doesn't require high flow or high pressure. You can do this at very low pressure and really with no flow at all. The only flow is determined by the movement of the piston. As I was saying, the consolidation of the bed, or the initial step when you consolidate the media into a bed, needs to be performed at a speed higher than the gravity settling rate. So most resins are going to settle, 100 to 200 centimeters an hour, maybe even less for high performance resins. So really, it's only the elasticity of the media that's going to provide resistance during the axial compression. So the last final compression after the bed has been consolidated and you're moving the piston into the bed can be performed at a really slow speed, like 50 centimeters an hour. It doesn't need high flow. It doesn't need high pressure. The other thing about dynamic axial compression is it's actually ideal for incompressible media. This is because the consolidation of the bed is performed with uniform plug flow. What that means is that you're not using you don't need to use the flow adapt or the high flow through the skid. The movement of the piston down gives uniform flow across the bed. It's just a plug moving down. Secondly, since you have really precise control of the piston height, you can position that flow adapter immediately above the bed or immediately on top of the bed without pushing into the bed and crushing the particles. So what are the pros of using a dynamic axial compression column? Well, it's a very versatile column design because it's easily scalable. There's the same principle that's used at 5 centimeters as at 2 meters. So secondly, you also get some improved bed homogeneity, since there's no flow changes, flow variabilities, or radial variations in the bed. It's also a very fast process. It's only one packing step. You have basically a slurry transfer step and a packing step, and that's it. The axial movement of the piston is in the same direction as process flow, so there's no radial variations to the bed in that case. Also, we use a thicker slurry with a dynamic axial compression compared to stall packing. So this is a smaller tank and less buffer, less footprint, etc. You can transfer the entire slurry into the column in some cases, in which case you don't need an overage. Lastly, this is not lastly, but it's a generally universal procedure for any type of chromatography media. There's usually very, very few changes that need to be made for this. It can also be automated to make sure that you have a reproducible process. There's obviously some disadvantages as well. The first is you must know the exact slurry percentage. This means you have to deliver a very accurate volume of slurry, but in chromatography processes, we can be accurate. It's not difficult to be accurate. Also, the height of the column tube must be at least 2 times the target bed height, in some cases more, to accommodate a 50% slurry. But I want to make it clear that none of these disadvantages have an effect on the quality of the packed bed. It really has to do more with your procedure for determining your slurry percentage. I want to show here some replicates that we did in my laboratory. As Herbert said, I manage the applications laboratory here at Bio-Rad. We used Bio-Rad equipment for automated packing. What we see here is a small column. This is a 20-centimeter column. This is a skid size 00, which delivers to 2 liters per minute, or 120 liters an hour. And we also have some packing pumps here. And all of these pieces of equipment are controlled by one software, so one user interface. And we can automate packing procedures and with this computer. So we see that there's a very reproducible asymmetry value and also a very reproducible reduced HETP. Now, if you're not familiar with reduced HETP, you should be. Historically, we've used asymmetry and number of plates, or number of plates per meter, or just HETP. Number of plates per meter, and HETP are all dependent on what the bead size is. So HETP could be, 0.013, or it could be 0.056, and you don't know how to compare those numbers because it's really going to be dependent on what the bead size is. So reduced HETP takes into account what the bead size is, and it gives us more of a universal comparison. So basically what it is it's the HETP divided by the bead size. And it's essentially the number of beads per theoretical plate. So in this case, we're close to about 2 beads per theoretical plate, which is the theoretical maximum, actually, for manufacture, or for packing chromatography resins. Now, generally, anything under 6 or 7 for a reduced HETP is going to be a good value. And this is true for any size bead, any size media, any column, and you can apply this number pretty universally. I do want to make a couple of comments about asymmetry testing. First of all, asymmetry and HETP ranges that you see in your media instruction manuals are ideal. These are what we as media vendors can get when we pack our columns well. But they're not always practical. There's a lot of things that are going to affect your asymmetry values. The flow rate, the type of solution you use. The flow rate is actually very important in this case. Where the proximity of the detector is, so is it really close to the column outlet? Is it further away? Where is the injection done? How is that done? Do you have to stop the flow before you do the injection, etc.? All of these things can affect your actual values. So you want to make sure that you set your acceptance criteria not based on what you find in a book, but what you actually get in your processing area. Your lot-to-lot consistency is more important than your actual values. And obviously the absence of shoulders and double peaks is important, but the overall values are not critical for most chromatography media, especially since, you know, anion exchange or anything that's using a step elution really only requires one plate in reality. So I just want to make a note about you don't always have to conform to what is provided by your media vendor. And with that, I would like to thank you for your attention.